So which formula should be used to answer part D, part C? What do you think? I think I'm kind of partial to the middle one. You could go. I mean, we know Q. So. So if we use this one though, we'd have 66.67 nanofarads divided by 2 times 48 volts squared, whatever that works out to. I got 7.6, well, let's say 76.8 microjoules. That's the total energy stored. And as a check, it'll be fun to do part D because we can check my answer to part C with part D. Because the total energy stored should be the sum of the energy in each. So we can calculate the energy in the 150 and the energy in the 120 using the Q formula, right? So like the potential energy in the 150, we can use the Q squared over 2C. So we've got, 3.2 microcoulombs squared divided by twice 150 nanofarads. And then the potential energy in the 121 should be, again, same charge, right? 3.2 microcoulombs squared divided by twice the 120 nanofarad. So let's work those out. So I got 3.2 times 10 to the minus 6, square that, divide by 2, divide by 150, divide by 10 to the minus 9. I get, all right, I think if I'm reading correctly, 34.1 microjoules. And the other one .7 microjoules. Notice that 42.7 plus 34.1 is about 76.8, which is what we got for the total energy. So that, if I'm wrong about parts C and D, I've been wrong in a really interesting way. So good. Now what's the voltage across each capacitor? So we go back to Q over C, right? So voltage across the 150 is equal to our 3.2 microcoulombs divided by 150 nanofarads. And that gives me what? I get 21.33 volts, which then tells me by logic that my voltage across the 120 nanofarad has to be 26.67 volts. How do I know that? Well, the sum of the voltages has to be 48. So if I've got 21.33 on the one, there must be the rest of the voltage on the other. Of course, you can check this also by, dividing 3.2 microcoulombs by 120. And since it's a smaller number, you get a bigger fraction. Right? So perhaps counterintuitively, the smaller capacitance gets the larger voltage. The larger capacitance gets the smaller voltage when they're in series like this. All right, so that's that problem. I don't know about you, but I'm kind of bored with capacitors. Want to go on? All right, let's see here. Well, let's see. Are there any other problems I should work in here? I'll talk more about the energy stored in the field in class Monday, probably. Well, let me see if I can find a good, more complicated problem to work. Yeah. Let's try to work number 53. I think if we can work that, then we've earned the right to go on to the next chapter. All right. Number 53 should kind of seal this off for today. I mean, we'll go to the other chapter after this. And of course, if you need to leave, feel free to leave. I'll just go on. It's like, okay. I talked to myself last week, Although I don't know if anybody wants to listen to me today, honestly. All right, so we've got this kind of interesting situation. We've got point A, and then you've got a capacitor, which they've called C1, and then you've got another capacitor over here, which they've called C3. You've got C2 in this vertical branch, and then you've got down here node B. They've called this one down here C5, and then C4 over here, and then they're connected. All right. And we're told that C1 equals to C5. I really like the way this problem is set up. This is a nice way to set it up. I really don't like when the numbers are put on the capacitors. It's like much more nice when they're written like this, I think. So you got your 8.4 microfarads and you got your 4.2 microfarads, and your VAB, the applied potential, which I've been writing as VB minus VA lately, is 220 volts. Well, that'll hurt if you touch it. So then the question is, what's the equivalence capacitance of the network, and calculate the charge on each capacitor and the potential difference across each. So basically find the charge and the voltage on each capacitor. All right. All right, so first order of business, we have to understand what we're up against. So here's the thing. We've got, I'm going to do it in stages, all right? So this is the same as, we've got C1, C2, C5. I'm not done anything to these guys, but I'm going to trade my C3 and C4 for C3 times C4 divided by C3 plus C4, right?
Would that be a series or
Yeah, these two are in series. So I'm putting those to this one. And because they're in series, that makes the capacitance smaller. And because these two capacitors are equal, notice the problem statement. C3 and C4 are both 4.2. What happens is this formula gives you a half. You get C3 squared divided by 2C3, which is just C3 over 2. So I can tell you what this is. This is equal to C3 over 2. Like that. That doesn't always happen, but it happens here. All right. So again, that was just to do some to explain what I'm doing. I'm collapsing this and this into that. All right. Everything else I left alone. Next up, I will squish these two together. So then I'll have my C1 and my C5 down here, and then over here I've got C2 plus C3 over C2. Right? But good news, C2 is equal to C3, right? So I might as well just write this as 1.5. Look at this, C3 over C2. That was a half, not a C2. 2. So this is 1 plus a half, which is 1.5 C3. All right. And again, just to be clear, what I did just now was I squashed this parallel combination into this. And now finally we're left with a series of 3. So this is equivalent to the single equivalent capacitance, CEQ, of 1 over C1 plus 1 over C5 plus 1 over 1.5 C3, all to the minus 1 power. And because we can make our life easier using algebra here, right? C1 and C5 are equal. So really all we're up against here is 2 over C1 plus 1 over 1.5 C3. Now you don't have to do things with algebra like I'm doing here, obviously. You could put in numbers and you could make it uglier if you wanted to. But I like to use letters, personally. So now we can see what we get. So I got 2 divided by, and the thing is, the units, as long as I'm consistent in my units, I know that I'm going to get a microfarad as an answer. So I don't put the microfarad into the formula. I just do 2 over 8.4, 2 divided by 8.4 plus 1 divided by parentheses 1.5 times 4.2. And then I reciprocate that. I get 63 over 25, but in decimals that is 2.52 or the microfarads. So there's the equivalent capacitance of the whole deal. Let's see here. This was number 53. I guess I should write that up here. 24.53. All right. And what do we get? 24.53. 2.5 microfarads. Yeah, okay. Pretty close. Probably round off error there. In the book, we didn't round off. Excuse me. All right, so then we want to find the charge. Then, let's talk about how do we find the charge. All right, so what's the total charge? Q total is, how do we calculate? CV, right? So C equivalent times my 220 volts. And that will give me what? I believe I get 554.4 microcoulombs, right? Are we good?
Wait,
Total charge?
yeah.
Now that will also be, so this is also going to be equal to Q1, and that will be equal to Q5, right? Is that what the book says as well? Yeah, Q1 is 550, and Q5 is 550. All right. It actually didn't ask for the total charge, right? But remember that the charge on the equivalence capacitor, you can kind of like, in some sense, you can look at it like this. I've got Q, I've got minus Q, right? And in some sense, that's this Q and this minus Q, right? And inside, there's a minus Q here, and there's a Q here, and there's a minus Q here, and there's a Q here. So like that, whatever you find as the charge on the equivalent capacitor, it is going to be the same charge on these three. So in particular, that means that there's, so we've got the Q1 and Q5. What's perhaps more interesting is that, so there is, Q2 plus, well, the thing is these are in series, right? So Q3 is equal to Q4. So whatever you want to put here, but Q2 plus Q3 has to be equal to Q1. But then how do you figure out how much goes here and how much goes there?
So why is Q2 plus Q3 equal 1?
Because the charge here has to be equal to the charge there. Because if this is minus Q, there has to be a Q2 and a Q, I mean, I don't have a good notation for this, but. So when they're in series, they have to share the same charge, but these two are not directly in series with that. So the charge gets split here, but we still have to have the sum of the charge on this and on that principle. But it's more complicated than that in truth, because of course it's actually the charge on here has to be the same as the charge here and the charge there. Not that they have to be equal, but the sum of the charges here and here have to match that in magnitude at least. Oh no. Oh. So we know Q1 already, but we don't know Q2 or Q3. But we also know that at this point, for me, the easiest way to do the problem is to figure out I really, the quickest way for me to see what to do at this point, and there might be other ways to do it, but I'll just tell you, like, so as I work at a problem like this, I just ask myself, what can I get to logically that will help me answer the question? And so the thing is, I have now deduced the charge on this one and that one. So I can figure out the voltage dropped here and the voltage dropped here, right? And whatever the voltage is between here and here, let's call it V2, right? I know that V1 plus V2 plus V5 has to be equal to my 220 volts. And because I can figure out Q1 and Q5. So Q1, V1 and V5 are Q1 over C1. So I've got like Q1 over C1 plus Q5 over C5, which is also Q1, right? Plus the voltage I don't know is equal to 220 volts. So I can solve that and tell me what the voltage is across the capacitors we haven't figured out the charge on yet. And if we're smart, as we do this calculation, we'll also figure out the voltage on 1 and the voltage on 5, right? Because voltage on 1 is Q1 over C1, voltage on 5 is Q5 over C5, right? So like Q1 is the 554.4 times 10 to the minus 6, right? And then I divide that by my C1, which was 8.4 times 10 to, oh, that was dumb. I could have just canceled the micros. Duh. I'm dividing 10 to the minus 6 by 10 to the minus 6 like a chump. I think C1 over Q1. What? Dude. No. V is Q over C. I did something wrong with my calculator. So the Q1 over C1, I've got 554 microcoulombs divided by 8.4 microfarads. The micros be canceling. 554.4 divided by 8.4. I get 66 volts. I'll write it up here. I get 66 volts here. All right. And for C5, oh, it's the same, right? C1 and C5, they both got the 8.4 mic. It's the same calculation again, right? So I've also got 66 volts down here. And if that's the case, I take my 220, right? 220 minus 2 times 66. This gives me 88 volts for my V2. So I got 88 volts here, right? V2 is 88 volts. Now that I know that, I can figure out what Q2 is. What's Q2? Q2 is 88 volts times C2, right? That gives me 369.6 microcoulombs, right? But remember that the charge here plus the charge there, right? The charge here plus the charge there has to match that. So that means that my Q4 has to be equal to my, 554.4 microcoulombs minus my 369.6 microcoulombs. which is equal to 184.8 microcoulombs. So that would be Q4. And because C3 and C4 are a series combination, that is also equal to what? Q3, right? That's also Q3 as well. So the only thing we haven't figured out so far now is the voltage on C3 and the voltage on C4. But that's easy to calculate now because we know the charge. So voltage is charge divided by capacitance. So I take my 184.8 and I divide by C3, which was 4.2. I get 44 volts up here, which means I don't even have to do anything else. Look at this. So I got 88 volts here. I got 44 volts here. Means I have to have 40 volt. Have to be 44 volts down here as well, because the sum of the voltage should match. And of course the capacitance C3 and C4 are equal, so that's also a symmetry there. So there you go. Man, this is quite a problem. We got 10 things defined, right? Voltage and charge on 5 different, wait a minute. Yeah, 5 different, so there's 10 total things defined. What an obnoxious problem. So if I have any good sense, when I ask this kind of question on the test, I don't ask for all 10 things. I like pick 3, you know? And you could pick 3 and make it interesting by just doing what? Like asking for the thing that you can't immediately see from the equivalent capacitance, right? Like it took us a minute to get to the inside of it. Like finding the voltage and the capacitance on C3 and C4 was actually, that it took us a while to kind of bore down into that. All right. So we have now reached chapter 25. And I think I'm going to call it a day, actually, because let's just stop here. Because I don't feel super horrible yet. So in the past, when I have gone past this point feeling sick,